Hey guys, Miss Muse here, just doing a quick warm-up with you today on thermal energy and energy transfer calculations, which were taught during Wednesday's class. So for those of you that were gone on Wednesday, Kara, Nicole, and Chris should be there to hopefully help guide you through the questions. But you may want to pause the video at that time when a question comes up, and then try the question yourself, and then proceed bit by bit. Alright, hopefully this works out. So the first question is, what will the final temperature of 250 milliliters of water at 22 degrees Celsius be if we add 2200 joules of energy to that system? So what I want you to imagine is that you have a pot on a stove, for instance, with about a cup of water. That's what 250 milliliters is, and you haven't heated it yet, but you're going to, and the amount of heat that you're adding to it is equivalent to 2,200 joules of energy. So, before we even start, I want to talk about just making sense of our answers, making sure that you understand that by adding thermal energy into this system, that we should expect an answer that is above 22 degrees Celsius, and anything that's below that makes no sense. And also, 2,200 joules of energy is really not that much, so we should not expect with that small quantity of energy for the temperature to increase substantially. All right, so first of all, what are we looking for? We're looking to see that final temperature. We need to talk about the fact that I've given you a volume of water, and that volume, 250 milliliters, is also equal to its mass in grams, and that's because the density of water is 1 gram per milliliter. So if we know the volume, we also know the mass in grams, and that's only true of water, and we can sort of use that as an estimate for substances that have a whole lot of water. So moving on. So of course we have the initial temperature at 22 degrees, and we have the specific heat capacity, which can be looked up in a table in your textbook. I want to say page 292, but you can look that up and make sure. But that's a value that is a constant for water and no other substance, and can be looked up in a table or researched online. And lastly, we know the amount of heat that's been added. So we're looking at the same question again here. And we're going to start out by we know that the tool we have to use in this case is Q equals mc delta T, Q being the heat, M being the mass in grams, C being that specific heat capacity, and delta T being the change in temperature, which we can also break down as, the final temperature, or T2, minus the initial temperature, or T1. Okay, and that way of demonstrating that is especially helpful if we're either looking for the final or the initial temperature, as we are in this question. Okay, so I've just gone ahead and I've subbed in all of the values in our givens, and now it's just a process of finding a way to isolate this T2 here. So it makes sense to me when I look at this to do some isolating first by combining these two values and then dividing that value into 22. And so when I do that, okay, here's the first step where I've just multiplied 250 by 4.18. Now I'm left with this 1045. So in order to isolate T2 minus 22, I'm going to divide both sides of this formula by 1045. There we go. That's what I get. And now the final step is to isolate T2 by transposing this negative 22 to the other side. Of course, that makes it positive, and so I end up with 24 degrees Celsius. Now I always need to remember that my significant digits need to be bang on, and so I look at all of the values in my initial question. None of them have more than 2 sig figs, and so my final answer is 24 degrees Celsius. All right, I'm going to move on to the next question. Okay, so in this case, this is a really similar question, so I'm going to run through it a little bit more quickly, but my own unknown is a little bit different. So I have 175 grams of an unknown substance, and there's a temperature change of 8 degrees Celsius when I add a certain amount of heat to it, and I want to know what the substance is. And so before I approach this question, what I need to ask myself is how am I going to figure out what this unknown substance is? And so given the question at hand, the only way of identifying the substance is by knowing its specific heat capacity, because every substance has a unique heat capacity, and that's something that I can look up. So I'm going to start by writing out my unknowns. Of course, what I'm really looking for is C, my specific heat capacity, which will allow me to figure out what the material is. And I know my change in temperature. Notice that I didn't really need to need to know what T1 and T2 were, my initial and final. That wasn't really relevant to being able to solve the question, so I'm moving on. Okay, my mass is 175 grams. There was no conversion there, and I always want to make sure that my units for mass are in grams and that my my Q value, my heat, is in joules for the table that's in your textbook, because of course my C value up here in the table we're using is in joules per gram degree Celsius, and the units need to correspond. There's my Q value. And so continuing to work on this problem, I've got my formula. Again, I haven't broken down my T2 and T1 because I'm just going to straight up sub in that 8 value there, at 8 degrees. So subbing everything in and isolating C by dividing both sides by that 1400, which is the product of 8 and 175, and dividing that out. So now that I have my C value, what I need to do is I need to go ahead and reference my table of specific heat capacities and see if there's any value that is close to this 0.896. And so I do that, and when I do that, I see that there's a value on the table that's pretty close to 0.90. I think it's 0.9. It's 0.900. So this is pretty much exact, but we need to account for some experimental error. So if you're ever doing a question like this and the answer is a little bit off, just know that that's reasonable when you're doing an experiment for real. So we know that 0.900 is the value given in the table for aluminum, hence our material is aluminum. Here we go, next question. All right, so this question is going to involve a little bit more of our thinking. So I'm going to read it out, and then I'm going to outline some basic ideas here. So we have a chunk of iron metal, and we've weighed it out, and it weighs 50 grams. And we've heated it so that it's lightning hot. And then around us we have a liter of water, and it's at about a little warmer than room temperature. Maybe it's like, the summer or something. And we're looking to see what the final temperature will be once I combine the two materials together. So again, we want to make sense of our answer. I know that my metal's at 375, and I know that my water's at 25 degrees Celsius. So I'm going to expect that my final temperature of that system is going to be between those two values. It can't be outside. That doesn't make any sense at all. And also, I'm also going to expect that the temperature is going to be closer to the 25 degrees than to the 375, because the chunk of iron is, of course, a whole lot smaller. All right, so this type of question we call a heat transfer question, because we know that all of the heat energy that's in that 50 grams of iron is going, well, not all of it, but most of it, a good chunk of it, is going to be transferred into water. But the value for the heat that is lost by the iron is equal to the value of heat gained by the water, right? So we're going to represent the amount of heat lost by the iron by putting a negative, because it's losing it, so we're going to make it a negative value. And since the water is increasing in its heat content, we're going to give its Q value a positive value, because, yeah, that Q value is increasing. Okay, so we can translate this, and don't be freaked out by this big thing here. All I've done is I've taken the other side of the formula, Q equals MC delta T, and I've written it down in the second sentence of this formula, or equation, rather. Okay, and I've just said, okay, well, I know that Q Fe is equal to M Fe C Fe delta T, so I'm just writing that out, and then doing the same thing on the right-hand side for water. Then I go ahead and I'm going to sub in all my known values, which can be, you can just grab that from the question itself. Now, the one thing that we haven't talked about is the fact that is T2. So T2 is not given for either, but this is the part of this is the crux of the question, which is that in the real world, that the final temperature of both the iron and the water should be equal. They should be equal if you let it reach sort of a equilibrium or a steady state. So that I'm going to solve this based on that assumption that the final temperature of the iron is the same as the final temperature of the water. So now the solving becomes more of an issue here. We want to clean this up a bit. So there are a few different ways of doing it. You can, multiply these guys out. And right here, I think that's what I did. Yes, that's what I did. Okay, then it looks a little bit more easily manageable. Now, you could apply the distributive property here and multiply both of these, negative 22.2 into the brackets on this side, and then do the same thing over here. But I just find it easier to just divide the left-hand side by the negative 22.2, and then that cleans it up to look like this. Okay, now it's starting to look simpler as we go here. So I'm going to now use the distributive property, but now I only need to use it on the right-hand side and not instead of both sides. And so I'm going to do that and multiply the negative 188.3 into the brackets. And so now I want to solve this as I would any other linear equation, which is by grouping my variable terms on one side and combining them, and then grouping my constant terms on the other. So I'm going to move the negative 188.3 T2 to the left-hand side and add it to my 1 T2, and then do the same thing with my constant terms on the other side, and that gives me that. Now the last thing, and this is unfortunately not going to show up in the screen because of the size of the screen that I made. I'm going to pause this for a second. And now I see that my final answer, when I divide both sides by the 189.3, I should see that my final temperature, if I evaluate that to two significant digits, is 27 degrees Celsius. Hope that was clear. If you have any questions, you can see me on Friday at lunch.